get started. So last time of class rather than lab, Arrow got to the point of talking about matrix multiplication. And it ended a little, I'm not sure what the right word is. I was no longer in the room, so I'm going to say awkwardly. Not that what he did was awkward, except that uncharacteristically he went faster that class than he usually does. So he got like partway through the next thing at a place where I know that some of you for whom it's new or you haven't seen it in a long time, you know, it felt like it wasn't completely clear. So I'm actually going to back up a little and go over that ground again, looking at it multiple ways, you know, hoping to make it clear for everyone. Okay? So first let's just back up to this part, which I think was fairly clear to everyone, where we got matrix multiplied by vector by thinking about what linear systems do. Okay? So just to review what you have in front of you, I gotta play my full. Arrow does everything wonderful, so I do my best to manipulate it. So I have one of these too. Okay, so you got a linear system. You know that the linear system to the sum of items is what it would have been to each item alone summed. Right? That's superposition. You know that if you scale the input, you scale the output by the same factor. That's homogeneity. So those are the rules of the linear system. So you do this, what seems like brain damaged, trivial thing over here, which is to say, if I took an arbitrary input to this linear system, I can describe that arbitrary input as the sum of each piece of the input. Here's the first piece, which is this little guy is the number 1 in that spot multiplied by the height of that little guy. This little guy is a 1 in that spot multiplied by whatever its height is. This little guy is a 1 in that spot multiplied by its height, which is, you know, -1/2 or whatever, this guy, etc. So if you take the unit vectors, this is a 1 in the first position. Think of that from your perspective. That's a 1 unit vector pointing in the x direction. This is a 1 in the second position, so that's a 1 pointing up. This is a 1 in the third position, so that's a unit vector pointing toward you. Well, there's 4, so I can't point anywhere, so that's pointing forward in time, let's say. Okay? So these are unit vectors representing the space in which the inputs live. And if you take each of those unit vectors and scale them by the length of that component of an input that you'd like to see what the linear system does, and then you add them together, you get this back. That's kind of totally obvious. However, it should also remind you of something that we have done. Let's see if mine work well enough, because they won't squeak. I don't think they will, but that should remind you. Oh, they're kind of dim. I guess I should red, blue, green. Use blue for them to deal with squeaks. Ooh, maybe I can avoid squeaks. Okay, so if we take an arbitrary vector here, v. We have a unit vector pointing down the x-axis, u1, and a unit vector pointing up the y-axis, called u2. And you've seen this projection thing before. And one way of thinking of that projection is that v is u1 scaled to be this long, plus u2 scaled to be this long. That's just another way of saying what I just said over there, in a geometry picture, instead of just making it in arithmetic. Okay? All right, so this vector is the same as the sum of these 4 vectors, each of which are unit vectors scaled. So what this picture is meant to say is if you want to know what a linear system does to any vector whatsoever, if the input is 4-dimensional, you only have to measure what the linear system does 4 times. And then you can predict what it does to anything else. And so those 4 times are, put unit vector in the x direction, see what you get. Put unit vector in the y direction, see what you get. Put unit vector in the z direction, see what you get. Put unit vector in the time direction, see what you get. Now, these 4 responses, we refer to them as impulse responses because we call these unit vectors. Another way to think of them as an input is an impulse in position 1. This is an impulse in position 2. So infinitely narrow height 1 input. Okay? So these are called impulse responses. If you measure these 4 impulse responses, you're done. You have completely characterized that linear system. You don't need to know anything else. You can now predict what that linear system does to any input. So for example, for this input, its output is this much of this guy plus this much of this guy. So these V1, V2, V3 are the same as these, which are the same as here's V1, here's V2, here's V3, here's V4. Those four numbers. Okay? Homogeneous superposition say, I summed four inputs, so I sum the four corresponding outputs to figure out what the output is. Those inputs were unit inputs, which I've got pictured here, scaled, which means that I scale their outputs. So I'm just using linear systems theory. So this, each one of these scaled by the right amount, and then added back together, that's the output. Okay? And then we followed that by, okay, I have a build here that I can skip because we've seen all this before. I'm going to skip ahead to where is the, yeah, this. Okay. So if I take those four, yep.
Would you also call the impulse vectors eigenvectors, or are they slightly different?
No, that's a whole nother thing, and it'll be a little while, it'll be a good while until the word eigenvector appears in this class. So that's a different thing. We'll get there, but not yet. Okay, so we had those four responses of the system to those four unit vectors. In the slide describing it, it used one of those spike plots, and so those four unit vectors were sitting horizontally. We now make a new representation of them, the one we'll use all semester, which is a matrix. So we'll take those four spike plots and put them down as the columns here. And so each one of these from that old thing was like 7 numbers. And so we now have a matrix which is 7 rows by 4 columns, called a 7 by 4 matrix. And that's, again, the summary of what the system will do to anything. And this Arrow went over, pretty thoroughly, which is a matrix times a vector is a linear system. It's a representation of the linear system. It's a description of what the linear system will do to any input. So if you take an arbitrary input, V1, V2, V3, V4, same V's I was showing just a second ago, what we're saying is 2 ways to think about it. One is from the inputs, what do you contribute to the output? So this unit vector scaled by V1, so 1, 0, 0, 0, scaled by whatever this number is, what it's going to produce is that impulse response, the first one, scaled by that number. The second number in the input is like a unit vector pointing in the y direction, multiplied by whatever this number is, and it will produce the second impulse response scaled by this number. So this way of thinking of matrix times a vector says each piece of the input, here's its influence on the output. And those influences sum. So this guy's influence, he's number 1, is to take the first column and just scale it by that. That's what his influence is in the output. That's what it contributes to the output. The third guy, his contribution to the output is to take this third column, scale it by that, add that into the output, do that for everybody, and that's what you get. Okay? Now, this guy is contributing to the output, and the output is going to be a 7 vector, right? We have 4 numbers in, but each of those impulse responses was 7 numbers out. These guys are 7 numbers, okay? And so you can ask, in the output, what's the third number going to be? Well, the third number going to be, in the output, the output's going to be 7 numbers. The third number is going to be, well, this guy contributed all of this, but in particular the third number got multiplied by this. This guy gets scaled by this guy, and in particular the third number is going to be this number times this, etc., etc. That brings you to the other perspective of matrix multiply, which says, not just what does each input do to the output, but what is each output number going to be? And what you just saw was, if I want to know the third number, I take this, 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 and I multiply by the corresponding guys in the input, and I add them up. In other words, I take the third row of the matrix, tip it over, multiply and add, otherwise known as we compute a dot product. Okay? So matrix multiply, the output is a dot product of each row of the matrix with the input. This dot product will be the first output. This dot product will be the second output, etc. Okay? Now, we want to get to where we were ending last time, which is not a matrix times a vector, but a matrix times a matrix. And I'm going to approach that as to what it looks like, how it works, why it works, and what it means. I'm going to approach that 3 different ways. Yeah?
Just to clarify with the matrix multiplication here. So the output of that computation is a 1 by 7 vector?
It's a 7 by 1. Usually say number of rows first. It'll be a column vector. In this class, almost always vectors are written as columns. Okay? So what used to be a spike plot that's horizontal, we're going to represent this way. Okay? Because all of our vectors, when something's on a matrix, it's a vector. Almost always, it'll be a column vector. It's a convention. We could redo all the math in this class and put the vector on the left and the matrix, the vector on the left and the matrix on the right. If you did that, our vectors would be row vectors. You could do that. It's just an ad hoc arbitrary convention. But the way we do it is the vectors on the right and apply matrices to them. So therefore, vectors have to be columns because of this compatibility of rows and columns and the multiplying. Okay. So I'm going to get at what's a matrix multiply multiple ways. First, just looking at it saying, here's the only way it could possibly work because this works this way. This is a matrix times a matrix. This matrix happens to have one column. Right? A vector is a matrix. It just only has one column. So if we're going to add more columns to the guy on the right, we're going to add them over here, and then over here, and then over here. We know what a matrix does to a vector to get you a new vector output. If I put another vector over here, the matrix is going to have to do the same thing, which means to get the second column of the output, I'm going to take this and do a dot product. Take this, do a dot product. Take this, do a dot product. There was no other way you could do a matrix multiply and have it be the obvious extension of what we have already talked about. Because if I'm going to put a matrix here, something with more than one column, that's going to be this, plus another guy and another guy, however many columns we want to have. And we already know what this does to this guy. So now we have to move it over and do it to this guy. So we're just going to do it again. Do exactly the same thing. This dotted with that. This dotted with that. So this has 4 across in our example. This has 4 down. And there's 7 rows. 1, 2, 3, 4, 5, 6, 7. Okay. Actually, that's a spike plot that might have made. I can't. Doesn't matter. Anyway, so 4 numbers dotted with 4 numbers. If we have a second one, again, we're going to have 4 numbers dotted with 4 numbers, and we're going to do that over and over again. So we're going to get a second set of 7 numbers. So let's see what happens. 7 by 4 by 4 by 1 gives you 7 by 1. Okay? The inner ones have to match because this is a dot product, so they have to be the same as each other, or it makes no sense. And the outer ones are what you're left with. Otherwise notice if I put another vector here, so that now my second matrix is 4 by 2. So now I have 7 by 4 times 4 by 2 gives you 7 by 2. Okay? So that is a picture that he showed at the end. I'm going to jump up to it and jump back. This one. So if it's 7 by 4, if it's 4 by, not this wide, but just 2, you get 7 by 2. If it's really wide, let's say this is 10, you know, you've got your 7 by 4, 4 by 10. Okay, the arrows compared to the numbers don't really match. And you get 7 by 10. This is this dimension and this dimension. Another way to look at it is, which we're going to get to, is we're thinking of these as linear systems, which means they're going to apply to an input. And so this dimension has to match the input that you're going to give to this system. Then go through all this stuff. And this dimension is the output you're going to end up with. And it may change the dimensionality, just like our 7 by 4 that we started with in the very first example takes 4 numbers in and spits out 7 numbers. Okay, so a single matrix that's 7 by 4 takes 4 numbers in, because you're doing dot products, so the thing over here has the 4 numbers, and spits out this many numbers, which in the example I've been using is 7. There was a hand. I just want to get through my sentence before. Is the hand on? Question got answered? Please interrupt me frequently. Sometimes I'll wait till the end of my paragraph, but I will answer, I promise. Okay, so now the next way to think about it is to think about it that matrix multiplication has to come out of what linear systems do. Okay. So we just said that any linear system, that was mine, and I'm not going to use it again because it doesn't work. I left the blue one over here. So let's get it. Okay, so then any linear system, let's say, oops. So like this linear system here, I'm going to call this linear system L1. Oh, I did it backwards, didn't I? That's going to be 2. This is going to be L1. So any linear system, say L1, can be summarized as a matrix. That's what we've been talking about, just still saying it's true. So that a vector input, so here's a V going into the system. So here's V. And suppose this one takes 4 numbers in and spits out 7 numbers. Let's just say that's the dimensionality, because that's the example we've been using all along. Okay? So that means L1 right here acts like a matrix. And it has rows that are length 4, and it has 7 such rows. Okay? This is just copying what I just did. But what I've just drawn there is, what if I take the output of L1 and wire it into the input of another linear system? Now, first thing you have to know is the output of this is going into the input of this. So it's got to be an appropriate input for this. And so that means we already know that L2 has to have 7 as its input. And so let's suppose that L2 has 3 as its output. Just making these numbers up. Okay? So L2 by itself can be described by a matrix. We know that. And we know what shape matrix this is, because it takes 7 as inputs. So L2 can be represented by a matrix where it takes 7 inputs, so it's obviously got 7 columns. It only has 3 outputs, so it's only got 3 of these. And that's a matrix that describes L2. Okay? Now we're going to put these guys in series, which means V is going to go to here, and it's going to become something new, which is going to be the, okay, so maybe L is a system, and I should call these guys M's for matrices. So this is M2, and this is M1. Okay? So V is a vector, it goes through the system, and what comes out here is M1 times V. Because that's what linear systems do. And M1 times V is a vector. How many numbers in M1 times V? How many rows in that column vector? 7. It's gone through the first guy. The output of the first guy has 7 numbers. It's dimensionality 7. Just like the examples we've been working with in the previous slides I've been showing. Okay? That now is a vector. Just put parentheses around it, saying we've just done that. That's the output of the first system. If we want to know what happens when V goes through both systems, we already have what it did going through the first system, and we already know what the second system does, which is it multiplies by this matrix. So we're going to do this. Okay? So that's just by definition. We're just composing, in the mathematical sense, we're doing composition of 2 systems. And we know what each one does. It does a matrix multiply with a matrix put in position on the left. And this will be true for any vector whatsoever. Now, this system, as a whole, as a box, I'll call it L. Actually, I think Errol called it L12. I maintain that's a linear system. Because the first guy's linear, and the second guy's linear. In other words, homogeneity. If I multiply V by 5, what comes to here gets multiplied by 5. And then it goes through another system. So what comes out to here also gets multiplied by 5. So the whole thing as a whole will be homogeneous. You scale the input by 5, you'll scale the output by 5. If you put A through here and get, A sub 1 and then A sub 2, so some vector goes through the first system, changes, goes through the second system, changes. If I put B through here, you get B sub 1, you get B sub 2. Okay? If I put A plus B in here, I know I get A1 plus B1 here. And if I get A1 plus B1 here, this guy's linear as well. I get A2 plus B2 here. So the whole thing has to be linear. And because the whole thing is linear, that means the whole thing is a matrix. So there exists a matrix, call it M12. And it has a shape. And its shape we know. Why? Because it takes 4 inputs. So this has to be 4. and it only produces 3 outputs, so this has to be 3. So that's M12. And so we're going to define that in the obvious way. We do M2 to M1 to V to get answers, which means we do M2 M1 to V. So first we define it by fiat. In other words, we define it assuming the typical associative law of multiplication. Right? You can move the parentheses around. A times B times C is the same as A times B times C. Right? You know that? It works for multiplication, it works for addition, it works for matrix multiplication as well. And at first, it's working for matrix times vector because I'm just asserting it. I'm defining it that way. Okay? And so that's a way to get at what matrix multiplication is. And by right of the fact that dimensionalities are changing this way, the shapes have to follow this. Because this number of columns has to be the number of items in your input vector, because you're doing dot products. And then this will give a vector this long by the time you're done. And then that's appropriate to match this, so these have to be the same as each other because you're doing dot products. And then the number of numbers you get out is this. So the overall matrix you've got is going to produce this many numbers from this many numbers. Over here, that example was, this was a 7 by 4, this was a 3 by 7, and we got a 3 by 4. It's the same thing. Okay? Yeah?
Can all linear systems be expressed as matrix operation?
Correct. In the finite dimensionality version, that's the only version we will do all semester. One can imagine linear systems apply to functions. So it's not exactly a matrix because you can't just count the columns. But for everything we do this semester, every linear system, matrix, linear system, identical. This is a representation of that. And you get it by putting in impulses along each of the axes and seeing what comes out. So once you collect the impulse responses, you're done. Those impulse responses are the columns of the matrix. You now know what the matrix is, and that's what the linear system does to any input whatsoever, so you're done. Okay?
Is it just for the course, or is it like in strict mathematical sense? Is it true?
No, it's strictly true. This is a theorem that we've already proven here. Now, not writing QED and fancy proof notation, but you basically have seen. That is true. It's a fact. It's a provable fact. Okay, so now let's talk about how matrix multiplies work. So I've said the way matrix multiplies work is if this is a vector you already know, you do dot product, dot product, dot product, dot product, and that's a column of numbers, you're done. But now if you add another one, you have to do the same thing again to the right of it. So I've asserted that, but now let's make sure we believe it. Okay? So let's come over here. So we have the matrix of the first linear system, L1, the matrix of the second linear system, and we'd like to say, oh, that must be represented by a matrix because it's a linear system. What is this matrix? What are the numbers in there? Now, how do we figure out what the numbers are in a linear system matrix? Well, I drew it this way, but I could just as equivalently draw it this way. Right? Matrices, it's 3 by 4. I'm just drawing lines to delineate another way of picking pieces out of it. Now this is a matrix that when applied to an input, V, which is 4 numbers. Remember, this matrix is 3 by 4. It takes in 4 numbers, spits out 3. Okay? Now, if I want to understand what this matrix does as a linear system, we've already said you understand what it does by seeing what it does to impulses. And what it does to an impulse in the first position is it produces these 3 numbers. So if we can figure out what these 3 numbers are, if we figure out what it does to this impulse, that's what these 3 numbers are. So let's figure out what does it do to this impulse. Okay? So it's 2 matrices being applied to an input. Okay? So let's give it a particular input, not just any input. Let's give it 1, 0, 0, 0. Okay, we're going to put in one of the impulses and see what happens. All right? So I want other colors, so I'm going to use colors to denote this. All right, So this system applies to this. It's going to produce 7 numbers. Okay? And what is going to happen? Well, I'm going to do this dotted with this, and I'm going to get this number. Because the others get multiplied by zeros. I'm going to do this dotted with this, and I'm going to get this number, etc. So what am I going to get? I'm going to get this. That's the vector I'll get out if I put in this unit vector. So that's what you get here if you put an impulse in position 1. You already knew that. That's the input view of matrix multiplication for L1. Okay? So now we've got this orange guy as a result of multiplying this matrix by this. Now this orange guy is now going to get multiplied by M2. So that's matrix times a vector. Dot product, dot product, dot product, dot product. We already know to do that. So what we've just determined is if you put in this, what you get out, otherwise known as this, where you get that is by doing dot product with the first column of M1, dot product of the second row with the first column of M1, dot product of the third row with the first column of M1. It's just like matrix times a vector, except it's the first vector. So I've just determined that this is exactly the rule I told you about matrix multiplication. It's just like matrix times a vector. But now let's pick an arbitrary one. There are 4 of these. Let's pick the third one. I'm going to switch colors. Okay? So I'm going to say, what's the, what happens if I do the third one? Okay, so now we're going to switch to a new input. The new input is going to be 0, 0, 1, 0. We're going to say, if I put a unit vector in the z direction, what happens? And by definition, that's going to be the third column here. This is what we're trying to figure out, is what's this guy? That's helpful. Okay, so let's walk through what happens. We put 0, 0, 1, 0. I do a dot product. 0, 0, 1, 0. I get this number, the third one. I do a dot product. I get this number, etc. Same logic. I'm going to get this vector. Again, this is just the input perspective of matrix multiplication for this particular input. Now, I've got a vector. It's the green vector. And I'm going to do another matrix multiplier. I'm going to do dot product, dot product, dot product, dot product. And so this third column is the dot products of this matrix with this third column. That's what I told you in the very beginning. So I was saying, if you add more vectors to the matrix on the right, all you're going to do is repeat what you were doing before, a little bit to the right. Now I've just proven that that's what you want to do. Okay? QED. Okay, so that's matrix multiplication. Matrix multiplication has to have the dimensionality match. The number of columns of the first guy and the number of rows of the second guy have to match because you're going to be doing dot products. So they have to be same length. But the other way of thinking about it is the output of the first matrix, the first linear system. This, the guy on the right, is the first linear system. He's the guy that applies to the input. The output of the first linear system has to match the input to the second linear system. Well, otherwise it makes no sense. You know, I'm a 4 vector. You take 5 vectors as input. You can't operate on me. You don't know what to do. Okay? Okay. Yes?
Is that when, like, so like in MATLAB, that would be like when it says like inner matrix dimensions don't match?
Correct. You do something wrong, MATLAB will not. Okay.
But that's the
Most of the time when you do something wrong, MATLAB will catch you and complain. Sometimes it'll do something generalized and then you'll have some debugging to do. But for that one, it will say matrix dimensions are incompatible or
And that would be like when the output of
the first one is the wrong
doesn't
set of
match
numbers for the
input.
next one. And do size of the first one and do size of the second one and see whether you are doing n by m times m by l. The inner ones have to match. Okay, so that's matrix multiplication. Let me see if there's anything here I need to do. Okay, so where are we here? Okay, so I want to skip ahead and come back to this stuff over there. I talked about this stuff. And what I want to skip ahead to is where we're headed, and then I'm going to start taking this diagram apart. Yeah?
Is it usually the case that we write a first system on the right-hand side?
Yeah, because this is the thing that's multiplied by the vector. So this is the first thing that hits the vector. This is the first thing that hits the vector. So yes, the order flips. When we draw diagrams of systems, we have this tendency, because in my language at least, you write from left to right, and so we have a tendency of having the arrows go to the right. But this is the input. This is the first thing that multiplies it. This is the second thing that multiplies it. So this is the second system. Okay, so you get that flip. With the other confusion about which way do we write things is we wrote these spike plots. They went both left to right. But when we turned them into a matrix, they went from top to bottom. That's just, it has to be that way so that dot products line up the way we're doing it. Okay, so these are conventions, but they're conventions everybody uses, so you just gotta accept those. Okay, so we have these matrices, we've defined matrix multiplication. Now we're going to delineate specific types of matrices and how they behave, and eventually getting to two very specific types that are going to be central to the rest of the semester. And those two types are diagonal matrices and orthogonal matrices. And again, Arrow started talking about this a little bit last time, but I want to start in the middle here. I want to start with the simplest matrix because we're talking about matrix multiplication as a type of multiplication, and you're used to multiplication, 5 times 3, it has these various properties, etc., etc. So I want to start with kind of the simplest matrices, the matrices that do simple things. So a diagonal matrix just means the only numbers that aren't 0 are on the diagonal. And I'm going to delineate, to start out, a particularly simple matrix. And that matrix is called the identity. So suppose we're in square matrix land, not 5 by 7, but 5 by 5 or 3 by 3. So let's take a 3 by 3. So 3 by 3 has 3 numbers here, 3 numbers here, and suppose it's a diagonal matrix, and suppose those numbers on the diagonal are all ones. So here is a very specific matrix. It is a matrix, so it is a linear system. It represents a linear system. It is 3 by 3, which means it takes 3 vectors in and spits 3 vectors out. It's just a matrix. So what does it do? Let's put an arbitrary v1, v2, v3, an arbitrary input in, and do matrix multiplication. Okay? Someone do this in your head and tell me what the answer is. You get back what you started with, right? Dot product, I get v1. Dot product, I get v2. Dot product, I get v3. Otherwise known as, if I call this matrix I for the identity, what we get is I times v equals v. Okay, so that's times vectors, and it acts like an identity. It doesn't change anything. Now let's do it in the world of 3 by 3 matrices. Okay? I despise this device. Okay, so we're going to do it in the world of 3 by 3 matrices, so now I need room for 3 more things. So, 1, 1, 2, 1, 3, 1, 2, 1, 2, 2, 2, 3, no column. So did I do that backwards? I did that backwards. 3, 2. Wait, what am I doing? Hello. Row by column. 1, 2, 2, 2, 3, 2, 3, 2, 1, 3, 2, 3, 3, 3. First of all, note the subscripting. Row, column. That's the standard. So if you see somebody referring to a matrix element, V, ij or mij, I is the row, j is the column. Did I do that right? I did that right. Okay, so now we're going to multiply that by I. What do we get out? Again, take a few examples, do them in your head. What are you going to get? Somebody say it out loud because you're whispering. What do you get out?
Original matrix.
Yeah, you get back what you started with. Pick an arbitrary element. This guy. Okay? It was 3, 2. How do I get the 3, 2 element in the result? This is going to be a 3 by 3, why? Because it's 3 by 3 times 3 by 3. So you get 3 by 3. The inner elements match, so you're allowed to do it. The outer elements are 3 and 3. Okay? Trivial, but it's the same rules we've been using. Okay, how do you get the third row, second column in the output? You take the third row, dotted with the second column. 0, 0, 1, dotted with these three guys, you get V32. So V32 is going to be right exactly where it used to be. That is true for all the entries. Try another one in your head. And also get some exercise in, this is a matrix multiply, okay? You're going to end up back where you started. Exercise for the reader. Do it in the opposite order. So what we just said is that I times m equals m. Also true, and it's equally trivial, just you've got to do what matrix multiplication is. That's also equal to m times I. So I in matrix world satisfies the role of what in numbers? 1. It is the identity for multiplication. Okay? So that's obviously a useful thing to know. If you end up with I, and oh, by the way, in MATLAB it's I, where you put the number of dimensions here. Okay? So you can create that matrix and call it to a function. Okay. So that's very nice. Now, where do I want to go from here? So we want to, so that's a nice, simple matrix that does something nice and simple. Now we've, in the 2 by 2 world, actually talked about other matrices. So let's go back to 2 by 2 for a bit and talk about some matrices that are a little fancier than the identity, but where the identity is an exemplar of these fancier matrices.
I have a question.
Yes, sir.
Why is the identity matrix so commonly used that there's a function just to create it?
That's an interesting question. Since it doesn't do anything, the question is, why would you ever want it? Because you will discover that in some things we do, you take a matrix that you have on hand and you add a little bit of the identity to it. That's a good way to take something that's misbehaving and get it to behave nicely. But we're not going to be there for a little while. So it is actually a useful thing to have. You wouldn't want to have the identity so you could multiply it by a matrix, because that's, doesn't do anything. But you might want to add it to something, and that would make it different in ways that we'll talk about. Okay, so in 2D world, we've talked about, suppose I have an arbitrary vector v, and suppose I have defined a coordinate system different than these x and y. I have a new coordinate system that I'd rather use. Okay? So that new coordinate system is going to be, let's say, u1, and perpendicular to it, u2. Okay? So I'm calling u1 and u2 a coordinate system. So first, let's get some facts straight. What is u1 dot u1? By definition, it's 1, because I called it a unit vector, and this is the squared length of the vector. So if the length is 1, the squared length is 1. Okay? Same for u2 dot u2. What is u1 dot u2? Say it louder. Because I called it a coordinate system, and I wanted it to be an orthogonal coordinate system, so I'm going to assert that I picked two vectors specifically to behave that way. Okay. Suppose I would like to represent v not as v1 and v2, which are the coordinates of v in the standard coordinate system that I have as the green axes here. But suppose I want to change my coordinate system and use u1 and u2 as my new x and y coordinates. So what are the coordinates of v in that new coordinate system? Dot products. Correct. We're going to do projection. Now, normally, dot product isn't completely doing what we want, but here it is doing what we want. We want to make it So I want this number here. I'm not sure what I'm going to call those letters. I'll think about that in a second. But I want to do this projections. So v dot u is the cosine of the angle between them, this angle. V dot u1 is the cosine of the angle between them times the product of their lengths. One of them has length 1. So I don't have to worry about that. So it's cosine of, call this theta 1. It's cosine theta 1 times the length of v. Adjacent over hypotenuse, here's the triangle. And so this length right here is v dot u1. Similarly, this length right here is v dot u2. Okay? So we've just re-represented v in a new coordinate system. So we can write that as, here's v, v1, v2, and here's our unit vectors. So let's put them in a matrix. And let's have this row be u1 and this row be u2. Okay? And that matrix multiply does exactly what we just did. It says u1 dot v, u2 dot v is the output. So we now have this new matrix sitting right here. And that matrix, we now know, takes any vector and restates it in this new coordinate system. One way to think about it is, suppose I drew the new coordinate system over here. Okay, so this arrow is now my new way of putting u1. I'm just drawing it differently because I'm thinking of it as a coordinate system. And it's my new standard coordinate system, not the one I started with in green, but the new one in blue. Okay? So let's think about this. The angle of v with respect to the old coordinate system was this big green thing. And now the angle with respect to the new coordinate system is theta 1. So here is v in u1, u2 coordinates, otherwise known as this matrix, which, what shall I call it? What's a good letter for an orthonormal matrix?
Capital U?
Huh?
Q.
Q? You like Q for orthonormal?
Usually Q, yeah.
Okay, I can't remember what the standard is. So I'm going to call this thing Q, because I'm told I should call it Q. Fine. So otherwise known as, this new vector is QV. Okay? So it's a new vector, it's the output. And what's the length of QV? Relative to the length of the vector we started with. The same. All we've done is change this angle to this angle. We've done a rotation. The axes were rotated counterclockwise. The vector got rotated clockwise. When you say the output vector, what's its new angle? Okay? Which means that this matrix Q, what it does is rotates vectors. Okay? It is a matrix whose columns, whose rows have length 1, and whose rows are all perpendicular to each other. Now, this is only a 2 by 2, so there's only one pair we're comparing. But take that concept and now blow it up to n dimensions. If I have a matrix whose rows are all length 1, and whose rows are all perpendicular to each other, that is called an orthogonal matrix. Probably should be called orthonormal because they're not only orthogonal, they're also normalized. They're length 1. But standard verbiage is to call it an orthogonal matrix. An orthogonal matrix. So, orthogonal matrices, basically, I'll talk about minor exceptions to this, basically do rotation. We've seen it in 2 by 2. I picked an arbitrary new coordinate system that's rotated relative to the original coordinate system. And I showed that if you re-represent a vector in that new coordinate system, all you're doing is rotating. Okay? That is true not just in 2D, that's true in ND, approximately. That's some approximations. that I will now delineate. So orthogonal matrices have that property. Now, let's talk about interesting aspects of orthogonal matrices. So let's take Q and multiply it. Arrow talked about transposes last time, yeah? I don't know if he didn't. I get confused with watching Arrow and watching Arrow on my computer as to which one happened when. Ooh, I'm a year off, and I wasn't even watching Arrow, I was watching me. That's even more scary. Okay, I can't deal with that. Okay, so we need to add a new, oh, I thought we got to that slide, but maybe we didn't get to that. Okay, don't need this anymore. So, minor matrix operation, called the transpose. Transpose just says switch rows and columns. So if I have a matrix that looks like this, this is 1, this is 2, this is 3, and let's call this matrix A. We have this matrix operation called the transpose, superscript T for transpose, where we just take what were rows and make them columns. So that A transpose element row I column J is the same as A element Ji. Just swap rows and columns. And for a 2 by 2, it's kind of obvious. Q transpose, this Q transpose just means take what's rows and make them columns. So that's going to be something here, which is U1, and something here, which is U2. What was a row becomes a column. Okay? Now, transpose can come up quite a lot. It's an operation we'll talk about a lot, but right now I'm going to use it in a very simple way. We have a Q, it's 2 by 2. We have a Q transpose, it's 2 by 2, which means we're allowed to multiply them. What do you get? So let's put Q times Q transpose. So Q has these unit vectors as rows. Q transpose just makes them columns. And the U's are the coordinate system. Do matrix multiply in your heads. Tell me what I get. Stare at it for a minute and think about it. Where do you get ones and where do you get zeros? Because those are the only numbers you're going to get. Say that louder. You get the identity. U1.U1 is 1. U1.U2 is 0. U2.U1 is 0. U2.U2 is 1. You get the identity. So Q and Q transpose are operating in a way that seems kind of familiar from arithmetic. You take any vector whatsoever and you do Q transpose to it, and then you do Q to it. And the net result of doing both of those operations is the same as doing this to it, which leaves you with what? It leaves you with what you started with. So Q times Q transpose, you know, we've already said, is the identity, which means whatever Q transpose did, Q does the opposite, leaving you back where you started. So in the example of the two-dimensional space that we've been working in, where I just told you that Q does a clockwise rotation, what does Q transpose do? By the same angle. It leaves you back where you started. So what does that make Q and Q transpose in arithmetic language? Makes them inverses. For the operation of multiplication, whatever Q does, Q transpose doing the opposite. Now, I've just told you Q times Q transpose is the identity. I have not shown you that that is also equal to Q transpose Q. I'm going to assert that, and for rotations it's kind of obvious, right? Just geometry. If this one's rotating it that way and that one's rotating this way, you can take a vector and rotate it down and then back up and be where you started, or you can rotate it up and then back down and be where you started. So at least for the 2 by 2 case, and you might imagine the n by n case, you're rotating this way and you're rotating that way, that this is true. One can do the math of proving that it works both ways. I'm not going to burden you with that today. If anybody's curious, I will definitely show you proof. It's not hard, but that was something I was going to skip. But at least for rotations, it should seem reasonably intuitive that rotations will work this way. Now, I keep asserting that this is a rotation. And let's go back to my coordinate system picture. It's not always just a rotation. So I had a U1 hat and a U2 hat, and I defined a matrix based on those two guys. What could I do using a different coordinate system than this one that wouldn't just be a rotation? What could I do using, instead of U1, U2, use something else? Let's leave one alone, U1 alone, and do something else for U2. There's only one thing I'm allowed to do, actually. What would that be? What's that? Stretch it? You know, I can't hear you. You know, I want an orthogonal matrix, which means that the elements have to be length 1. So I'm not, stretching it is not in the list of things I'm allowed to do. You can flip it, okay? So instead of having this be U2, I can have this be U2. That's legal. That'll give me a matrix. All the rows of the matrix will be length 1. All the elements are perpendicular to each other. This used to be perpendicular, so this, negative U2 is certainly perpendicular. That's fine. But I've done a flip, which means now all of a sudden all my second coordinates will be negated. So that's not just a rotation, it's a rotation and it's a flip of the new coordinate. Okay? That's legal as an orthogonal matrix. It's not just a rotation, so you're also allowed mirror reflections on any of the axes, on any combination of the axes. Those are still orthogonal matrices because they will not change this property. This property will still be true. Now let's understand that this property works when we're in n dimensions. And it's all still true, and we can flip things and it's all still true. So suppose we have an orthogonal matrix that's more than 2-dimensional. Let's say we're working in so many dimensions that I can't draw them. Okay, so we'll work in 4. So we've got, the way I originally defined Q was as a row, a bunch of rows. So here's U1, U2, U3, and U4. Okay, so we're now in 4D. And here is something that I assert is an orthogonal matrix because I have a 4D coordinate system. Here's 3 of the dimensions, and the other one I can't show in the room. Okay? So this times itself is 1, this times itself is 1, this dotted with itself is 1, this dotted with itself is 1, because these are length 1 guys. These guys are all perpendicular to each other, so all the cross products as dot products will be 0, because everybody's perpendicular to everybody. Here it is in 3 dimensions, but I have to have the 4th one that I can't show you. Okay? And so let's think about doing this. Except I now have 4 of them, 3 and 4. I now have 4 of them, 3 and 4. And again, they're all perpendicular to each other. So what am I going to get? I'm going to get an extra one here, an extra one here, an extra one here, and everything else is going to be 0. I'm going to get the identity again. Okay? So everything I just showed you in 2 by 2 intuitively extends to any number of dimensions. Okay? So an orthogonal matrix. Did I miss one? No. Oh, I got an extra one. This one's extra. There we go. So, orthogonal matrix, by definition, is some kind of change of coordinates, which means it leaves you in the space you were already in, which means that the input dimension and the output dimension have to be the same, which is to say, if you're going to call something an orthogonal matrix, by definition, you're talking about something that's square. Okay? It's something that's changing coordinates. So if you're in 3D and you have 3 coordinates of the vector you started with, you're going to have 3 coordinates of the vector you end with. Okay? So orthogonal matrices have to be square. The rows are orthogonal unit vectors. That's the way I defined it. But I showed you, I only did half the proof, that when you transpose it, you get somebody that also acts like a rotation. And because it acts like a rotation, the rows of that have to be unit vectors that are orthogonal to each other. So what I've just shown you is I built a matrix such that the rows have this nice property, their coordinate system. But having done that, for free, that's subtle, but for free, if I take this set of orthogonal vectors, and now I look at the columns, meaning the first element of each of those vectors, the second element, those guys are also length 1 and orthogonal to each other. And one way you know that, at least in the 2x2 case where it's kind of obvious, is the matrix we started with, the rows were what got you coordinate rotate me this way. And the columns are the coordinates that say rotate me that way. So they have to act the same way. They have to have the same properties. They have to be an orthogonal matrix. So if this guy's orthogonal, its transpose is also orthogonal. This guy is a rotation plus flipping occasional axes. You transpose them. The rows of that are also a new coordinate system that are orthogonal, possibly with some flips. Okay? So that's what this says. Now, what does it do? It does rotations, and occasionally it'll take a dimension and flip it, so go around the axis, what was plus becomes minus. So any vector, if I rotate it, and then maybe flip it, what happens to its length? Nothing happens to its length. So length is preserved. It's an operation that whatever it does to a vector, spinning it around, pointing in other directions, flipping plus or minus on 3 of the dimensions but not the other 5, whatever it does, length doesn't change. It also doesn't change angles between 2 vectors. Here's 2 vectors. I rotated them both. I flipped them both. They're saying rigidly connected to each other while all this is happening. Okay? So it preserves angles, it preserves dot products. That part is probably relatively easy to show. And the last thing I talked about is that the transpose is its inverse. That was just this, the dot products give you the identity. I asserted that it worked either order of multiplying by saying it's just doing rotations, and rotations undo each other in either order. Okay, so that's a set of matrices that are going to turn out to be extremely useful for the entire semester, and the first way it becomes obvious will be the next lecture that Arrow gives on Tuesday. Okay, now, next set of matrices that are useful to talk about are those that are mostly filled with zeros, except along the diagonal. So we've already met one of those. That's the identity matrix. Here's an exemplar, poorly written. Okay? So there's stuff on the diagonal. There's no stuff outside the diagonal. If the stuff on the diagonal is 1s and the other stuff is zeros, and if it's a square matrix, that's I. So that's an example of a diagonal matrix, but it's a very, very special case. We're going to talk about diagonal matrices of any arbitrary size and shape and numbers. So now I define a diagonal matrix D for diagonal. Beans over here. Carry them with me. So if we have a diagonal matrix, what I'm saying, so I'm going to have a diagonal matrix called D, and it can have an arbitrary shape. For now, I'll have it be wider than it is tall, but it doesn't have to be. I'm just picking one out of a hat. And I'm saying it has stuff on the diagonal and nothing anywhere else. Nothing meaning zeros. So this is a 0, this is a 0, this is 0. These are all zeros. And here, it doesn't have to be non-zero, but it's allowed to be. So in other words, this element here is D11. This element here is D22. This element here is D33. So only the elements of D, where I equals J, same row, same column, are allowed to be non-zero. That's the definition of a diagonal matrix. Yes?
But elements in the diagonal can still be 0.
They can be. Dij can be arbitrary. It's just Dii can be arbitrary. dij for j not equal to I must be 0. That's just the definition. Okay, now it's a linear system because it's a matrix. Q was a linear system because it's a matrix. And Q as a linear system, we've already described, is a rotation plus maybe some flips. It's a linear system. Why? Here's a vector, I rotated it. Here's a longer vector, I rotated it. I got a longer vector pointed in the new direction. And it's also the case that, because the matrix multiplied, when you add two vectors, well, this guy is going to get rotated, that guy's going to get rotated, so their sum is going to get rotated by the same amount. Okay? So linear system works for orthogonal, and obviously works for diagonal also because it's a matrix, by definition. So let's see what that matrix does. All right? So I've written one that's got 4 rows and a lot of columns. It operates on big long vectors. It makes vectors out that only have 4. So let's give it an arbitrary vector. V1, so this is V, which is V1, V2, V3, V4, blah, 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 blah. Okay? It's break time. I will return to this in 3 minutes. When the big hand is on the 8. There is no 8 on that. We're talking about diagonals, we're talking about orthogonals. This picture here is meant to be a Venn diagram. You'll notice that the identity matrix, among others, is sitting in the intersection of this stuff and this stuff, right? Because the identity matrix doesn't have any 0 stuff off the diagonal. I've just introduced what a diagonal matrix is. So the identity matrix is certainly an example of a diagonal matrix. And an identity matrix also has rows that are all length 1 and rows that are all orthogonal to each other. All dot products in an identity matrix are either 1 when it's a row dotted with itself, or 0 when it's a row dotted with another row. So an identity matrix is an orthogonal matrix. It does a rotation by how many degrees? How many degrees does a vector get rotated when you multiply it by I? 0. It doesn't get rotated at all, right? So it is a rotation, just a trivial one, okay? So I'm just pointing out, we talked about the identity matrix. It has the properties of both of the things that we're talking about today, okay? Secondly, as I was defining diagonal matrices, I say that the main thing about a diagonal matrix is that off the diagonal, everything has to be 0. On the diagonal, it could be anything. So for example, suppose all those DIIs are 0. That's a matrix that has nothing but zeros in it. It is a diagonal matrix, because off the diagonal, everything's 0. It is a horrifying matrix, because whatever you give it, the output is 0. Okay? So we have, in arithmetic of numbers and multiplying, we have, reciprocals, right? 5 and 1/5 are inverses. And we've talked about the transpose of an orthogonal matrix acts like an inverse. You rotate this way, you rotate back, you end up back where you started. You multiply by 5, and then you multiply by 1/5, you end up back where you started. And so a 1-by-1 matrix, which is a scalar, has that property, right? If that 1-by-1 matrix is 5, its inverse is 1/5. Okay? And the other thing you have in arithmetic is the 0, the thing that maps everything down to nothing. All right? All information is lost when you have this thing whose value is 0. A matrix filled with zeros behaves that way. And in particular, if you live in the world of square matrices, where the inputs and the outputs are the same, where the matrices can all multiply, are all allowed to multiply by each other, the matrix filled with zeros in that set of stuff acts like the scalar called 0 in the set of stuff of multiplying scalars. So I'm waving my hands at what abstract algebra would do, which is to say matrix multiplication is an operation. It has various things that it satisfies. It has, in square matrices, there's a thing that acts like the identity, and there's a thing that acts like 0. But, as we shall see, there are not always things that act like inverses. Obviously, 0 doesn't have an inverse, but even with scalars, 0 doesn't have an inverse. If I multiply by 0, I can't unmultiply and get back the number you have, because you're at 0, you're stuck. Arrow was talking about that with dot products. Once you get down to 0, you've lost information. Anyway, okay. So we have this, over there? Over there. Okay, so let's go with diagonal matrices, then I want to go back to orthogonals in a bit and clean up some stuff that I should have and could have said and didn't. Okay, so we have this diagonal matrix. An arbitrary one. I don't know what these numbers are, I'm just calling them D11, D22, etc. Okay? And it takes big long vectors, here's a big long vector, and it produces 4 vectors, because there are 4 rows. Okay? And so let's see what you get out. So we do dot products. And these dot products with diagonal matrices are particularly easy, because there's a lot of zeros all over the place. So we take this guy, dot it with that. These guys all are going to get matched up with zeros. So they're thrown away. So what you get in the first position is D11 times V1. What you get when you take the second row and dot it, everybody gets hits with zeros except the second guy. So you get D22 times V2. Third guy times the third guy, you get D33 times V3, and D44 times V4. So as a linear system, but thought about in geometry. So I have this vector I started with. It points, somewhere. And it's got a first coordinate, second coordinate, third coordinate, fourth coordinate, and a whole bunch of other coordinates. By the time I get through the system, that whole bunch of other coordinates, whatever information they had, is now completely gone. You see no V5 over there. You see no V18. They're all gone. Not only are they, set to 0, they don't contribute to the output at all. Not only that, but the first coordinate only contributes to the first one. The second one only contributes to the second one. Third, what it contributes is just scaled by what was on that diagonal. Okay? So what a diagonal matrix does is it takes, this vector that's got all these coordinates, it takes the first few coordinates, the ones where D has a chance of being non-zero, and stretches them. It could multiply the first coordinate and stretch it out by a factor of 2. It could multiply the second coordinate and squeeze it by a factor of a half. It could take the third coordinate and turn it upside down, multiply it by -1. That's what it does. If it is wider than it is tall, then it's taking a whole bunch of the original vector and throwing it away. It's reducing dimensionality like any wider than it is tall matrix always does, but it's reducing dimensionality by taking dimensions of the input and ignoring them. Totally throwing them away. Okay? Suppose, instead, that it's taller than it was wide. So now I'm going to make it 4 columns. But I'm going to give it extra rows. So I still have this D11, D22, D33, and D44 sitting there. But now everything else down here is off diagonal, which means all this stuff is 0. I'm not even going to write lots of little zeros and get the wrong number of them. I just put a big 0 saying there ain't nothing here. Okay, so now let's do our dot products. First one times the first one, I get what I had before. The second one times the second one, I get what I had before. This is going to happen 4 times. So the first 4 entries are going to be exactly what I had before. And then I'm going to have a whole bunch of extra entries because this is going to produce this many outputs to 4 inputs. And those outputs, way down here, are all going to be 0. So when a diagonal matrix is taller than it is wide, like any system that's taller than it's wide, it is producing a greater dimensionality on the output, this is the output dimension, than it gets on the input, but that extra dimensionality is worthless. It's all filled with zeros. Okay? So it's putting a 4-dimensional vector in a 12-dimensional space, but where dimensions 5 through 12 are all 0. Okay? And what it does to the other dimensions is stretches them by this amount, by this amount, by this amount, by this amount. Sorry. If that diagonal matrix happens to be square, so now we're at a 4 by 4, so I've got rid of all this stuff down here. We can think about it geometrically as to what it does. It takes the first dimension, stretches it by that. Takes the second dimension, stretches it by that. Takes the third dimension, stretches it by that. Now I need my device. So we'll do it in 3. Arbitrary vector pointed in some arbitrary direction. suppose D11, which is the x-axis, is 1. So it got to here, it still gets to here. Suppose D22 is a half. That means the y-axis, which was up here, gets halved. So we go down by a factor of 2. Suppose D33, which is the z-axis, is -1. Okay? So we had a vector that was pointing over here. It's now pointing in a completely different direction. It has a completely different length. Exact opposite of an orthogonal matrix. A diagonal matrix can mess with the direction of vectors. It can mess with the length of vectors. If you have two different vectors, the angle between them can change. And this is kind of obvious by right of the fact that when we went from, let's see, it was y that went down, right? And so the angle between this vector, and then it flipped. So let's talk about this vector and its projection onto the horizontal plane. So these are two vectors. They have an angle. And in this operation, I left the x alone for both of them. I lowered this guy by half, so now the angle between them changed. And then I flipped them over here, which didn't do anything to the angle between them. So by the time you're done, you end up with a different angle. Okay? So it doesn't preserve angles, doesn't preserve lengths, doesn't preserve directions, doesn't preserve anything. But what it does is incredibly simple. It just stretches the space. It's like rescaling all the axes independently. It's exactly what it's doing. It's scaling the x-axis by one thing, the y-axis by another, the z-axis by another, and the t-axis by yet a third. Okay? So it's as if I have this vector, and it lives in this 3D space now. And what the diagonal matrix does is it acts like this 3D space is made out of rubber. And I'm going to take the x direction. I'm not going to stretch it, compress it, do anything, because that number was 1. I'm going to take the y dimension. I'm going to take my rubber space and squish it towards the origin. Things below the origin go up, things above the origin go down. And then I'm going to do this thing that's not like stretching. I'm going to also do a flip. Okay, so things that are positive go negative, and things that are negative go positive. So that's what a diagonal matrix can do. It is a very simple operation. Arithmetically, what it's doing is so obvious. It's just independently operating on the coordinates that correspond to the diagonal, and any other coordinates, are full of zeros. So either you add a bunch of zeros at the end, at the bottom of your vector, if it's taller than it's wide, or if it's wider than it's tall, it takes all the extra stuff in this vector and throws away those dimensions. Okay? So diagonal matrices don't have to be square. The definition is that any entries in such a matrix off the diagonal are 0. You can squeeze and stretch along these things and also flip them. If it's not square, it either adds a bunch of dimensions but fills them with zeros for the tall ones, and for the wide ones, it deletes dimensions and just throws that information away. Now, let's talk about inverting, because I've come up with this concept of what do I mean by a matrix inverse. A matrix inverse is something that undoes what you just did and leaves you where you were. Now, if you're going to leave you where you were, you have to think about dimensionality as to what you mean by inverses. So let's start, and actually I think it's the only place I want to go today, because we don't really deal with this so much in this class. But let's start with square matrices. So a diagonal matrix that is also square, the identity is an example of one of those. So a diagonal matrix that is also square, here's a diagonal matrix D. It's a bunch of zeros, and then D11, D22, let's say D33. So it's a 3 by 3. Okay? So there's a nice example of a diagonal matrix. So what it does to the first element is it multiplies it by D11. What it does to the second element is it multiplies by D22. What it does to the third element is it multiplies by D33. So it just does some stretching, possibly some flipping. That's all it does. So if I take the x-axis and stretch it by a factor 2, and now when I get back where I started, what do I want to do? I just doubled things. So if I want to get back to where I was, what do I want to do? You want to have it. The inverse. 1 over d1. I just tripled all y's. How do I fix it? 1 over 3. So I want to do 1 over d22 and 1 over d33 and a bunch of zeros. We see that that matrix multiply is going to get you the identity. Do the matrix multiply. This row times this column gives you 1. This row times any other column, no non-zero things match. This second row times this second column, that's d22 over d22, gives you 1. This third row times this third column, 1 over d33 times d33 gives you 1. Equals EYE of 3 in MATLAB notation. Okay? So inverting a diagonal matrix is really easy, 1 second, unless you can't do it. When can't you do it? When any of those guys are 0, there's no such thing as the reciprocal. Question?
I was supposed to ask that.
That's why I held you off. I'm not always right, but occasionally I get lucky. Okay, so notational things. I'm using D for diagonal, which we'll often do, just as a way of reminding you that the matrix we're currently talking about is diagonal. I put a superscript -1, like we do in arithmetic, to say inverse. Right? When I have a scalar who is A, its reciprocal, sometimes we write as 1 over A, but sometimes we write as A to the -1 power. And so that -1 power means inverse. Okay? So diagonal matrices, if those diagonal entries are all non-zero, they have an inverse. And the inverse is obvious. Just write down all the reciprocals. Okay? And that obviously gets you back where you started. Meaning, treating it as a linear system, if I put a v here, and I multiply it by this, which means I take all the coordinates and stretch them or squeeze them or invert them, as this implies, if I now unstretch them and uninvert them, I'm back where I started. These two guys multiplied are the identity matrix, which means if I put v here, I get v back. So that d inverse acts like the inverse of d. So if you apply d to something and then you apply its inverse, you end up back where you started. And vice versa, in the other order. I could multiply v by this first, and then that. I could put these guys in the opposite order. And so that's a true inverse. Doesn't matter which one I do first. You can do it in either order. Okay? Okay, so we now have diagonal matrices, and we understand what they do. We also have this notion of an inverse for a diagonal matrix, which only exists if that matrix has all non-zero diagonal entries. We're going to be talking, starting next time pretty much, about the idea of, okay, maybe I don't have an inverse, but let's try to invert as much as I can. Okay? In arithmetic, we don't have that concept. You either can invert it or you can't. With matrices, sometimes we want to invert as much as we can, giving up on, it sounds like that Alcoholics Anonymous prayer, right? Not change the things I can't, but change what I can. Okay? So, this is D, this is D inverse. But suppose I want to invert it, but occasionally some of these guys over there were 0. So let's say D22 is 0. Well, then I can't do this. So I don't do this. I just stick a 0 there because there's nothing I can do about it. Okay? So that multiplied by that will not get you the identity because the middle guy is 0 here, it's 0 there, you're going to get a 0. You're not going to get the identity. You're going to get the identity wherever you can and give up wherever you can't do anything about it. Okay? That's going to be a very, very useful concept. We refer to it in a much more general state as a pseudo-inverse. It's not a real inverse, it's just invert that which you can, fix what you can, and give up on what you can't. So what's a diagonal matrix do? It takes some axes and stretches them, and we're going to put them back. It takes other guys and squeezes them and maybe flips them, and we're going to put that back. But it takes some axes and deletes them and collapses them to 0. You can't fix that. So that axis you give up on. And this is giving up. Just put a 0 there. Okay? So that'll be a useful device that we're going to run into quite a lot. All right, so arbitrary shape, they either create, they squeeze and they stretch and they flip. If it's non-square, it's either deleting axes that used to be there. So if it's wider than it is tall, then it's deleting axes, but stretching and squeezing the ones that remain, the first few. And if it's taller than it is wide, it's creating axes, but it's creating useless axes because they're filled with zeros. Okay? And we've just talked about the inverse, which is you just do all those reciprocals. And we also talked about the pseudo-inverse, which is you do reciprocals when you can and give up and put a 0 when you can't. Okay. What else can go in the middle here? We said the middle here is things that are orthogonal, meaning all the rows are length 1 and all the rows are perpendicular to each other. Things that are diagonal, so they have this form. There's only stuff on the diagonal and nowhere else. So suppose we're in a 3x3 world. We're in a 3x3 world, and obviously 1, 0, 0, 0, 1, 0, 0, 0, 1, otherwise known as the identity matrix, or I of 3, that's obviously in that intersection. There ain't much else in there. What else is in there?
The negative ones?
Plus or minus, plus or minus, plus or minus. Done. Yep. Because the minus doesn't affect any of the properties we're talking about. The minus, that's still, if this is minus, that's still length 1. And it's still orthogonal to everybody else. And anything else you can't get away with because you've changed the length or you have something off the diagonal. Okay? So the intersection is the identity plus allowing yourself to decide that an axis that used to go up now goes down, which is what a minus 1 does. Okay? Maybe you had a right-handed coordinate system, you remember that from physics, and now you have a left-handed coordinate system, or whatever. Okay, let's go back to orthogonal matrices and what they do. All right. Forcing myself to use only this board. Keep doing that. So, I said I wasn't going to prove this, but the geometry is useful, and I've forgotten that we tend to do this, so I'm back to it. So, suppose we want to pick a coordinate system. So, u1 hat, u2 hat, u3 hat. Okay? And suppose, well, actually, let's do it in 2 dimensions so I can draw the geometry. Just 2. All right. And so we make ourselves an orthogonal matrix Q, which has u1 hat as the first row and u2 hat as the second row. That's my matrix. And we've talked about what matrix multiplying by a vector does. So here's an arbitrary v. And what does it do? Well, I'm just regenerating the diagram I had before. Suppose this is u1 hat. Suppose this is u2 hat. They're both length 1. I'm gonna. If you use the colors I use, I'm now inverting them, so this can confuse you utterly because I had green here and blue for what I'm about to do, and now I've swapped them. Okay, so here's my arbitrary v. Okay, and matrix multiply. So here's my arbitrary v. 1, v2, and I'm doing this matrix multiply. And what is that? That's a dot product here, which is to say projection onto this. This is something that was on the board earlier in the day. And the second one is u2.v, which is projection to here. Okay? So that's what this matrix does. Okay, so now let's think about, and what we pointed out was that if I take Q transpose, and I do Q times Q transpose, so Q times Q transpose, say, so that's the same as this guy, U1, this way, U2, this way. That's Q. I multiply it by its transpose, which is U1, U2. I obviously get the identity. This is from much earlier in today, right? Dot product is 1, dot product is 0, dot product is 0, dot product is 1. I just got the identity. I asserted that you can do it in the other order. So let's think about what happens if you do it in the other order. So let's talk about Q transpose times Q applied to some vector, V. Okay? That's the other order. I asserted that doesn't do anything. Let's actually play out what it does. Well, the first part is Q times V. That's on the board. Right? Q times V is take V and represent it in the Q coordinate system. I got it right under my arm. Okay. All right. So that Q times V gives you a vector. It gives you a vector that has, I've got it right here, and I've got it up here. And the elements of Q times, this is Q times V. I already wrote it up here. And it gives you a 2 vector, which is the one in the new coordinate system. And that 2 vector has elements which are U1 hat dotted with V and U2 hat dotted with V. That's the vector you got out. Right? Just make sure. Do a dot product, do a dot product. Okay, that's a new vector. Now, we want to multiply by Q transpose. Q transpose times QV is the same as Q transpose times the result. You know what the result is. Here it is. U1 hat dot V, U2 hat dot V. These two numbers we're talking about are this projection and that projection. Okay? I haven't done anything new yet, but now I'm going to say what happens when you multiply by Q transpose. And so, what's Q transpose? So, Q transpose is this guy. I'm going to transpose Q, so it means the unit vectors are now vertical. So let's write it that way. So Q transpose is U1 hat as a column vector, U2 hat as a column vector, times this thing. U1 hat dot V, U2 hat dot V. Okay? That's a matrix times a vector. Now, you'll notice the matrix is now written as columns, not as rows. And you remember that when we talked about matrix multiplication, there's 2 ways to think about it. One is, the way you get the outputs is you do these dot products with the rows of the first matrix, right? The other way to think about it is the columns are the contributions that each element of the vector make to the output. So this column is going to contribute to the output by this much. And this column is going to contribute to the output by this much. Okay? So I'm going to write that down. I've run out of space. People are going to be looking through each other's heads. Equals, equals. I'm going to move the answer up here. I'm going to take this column, which is U1 hat, and I'm going to scale it by this much. U1 hat dotted with V. I'm also going to take the second column, U2 hat, and I'm going to scale it by this guy, U2 hat dot V. And I'm going to say, what does that equal to? Let's go back to the diagram. I'm going to take U1 hat, and I'm going to scale it by this number. What is this number? This number is the length of that. So this first term right here is this unit vector scaled up to make it all the way to here. That's the first term. The second term is U2 hat, that's this unit vector, scaled up to be this long. And this long is the projection. So that's this. Then I'm going to take those 2 squiggly written vectors and add them back together. What do I get? I get V. I get back where I started. And that's true no matter what V is. So that Q transpose times Q, I proved Q times Q transpose is the identity matrix. Now we're doing Q transpose times Q. And what I just showed is that Q transpose times Q, whatever it is, it doesn't matter what you give it, it doesn't do anything. There's only one matrix that does that, and it's the identity, which is to say Q transpose is also Q's inverse from the left. Q is Q transpose inverse from the left. We show that just by doing dot products. It was obvious. You can flip it, and the geometry says that also behaves that way. Given that, you know that Q transpose is an orthogonal matrix. This effectively is the proof I said I wasn't going to do today. That you gave me a bunch of unit vectors, and I made them the rows of a matrix, and the matrix now has it such that the rows are perpendicular to each other. I've just said Q transpose acts the same way. And so therefore it has rows that are length 1 and perpendicular to each other, which means Q originally now has columns that are length 1 and perpendicular to each other, even though that's not the way you built it. Okay? You give me a coordinate system, and Q transpose is kind of like the inverse coordinate system. It does the inverse thing to input vectors, and I just showed that that's what it does. Okay. Ask questions. That was a lot of stuff. Not to mention that I'm fearing that I got to the end of everything I was meant to do today. Arrow and I are trading it off in our usual way again. He goes at one speed, and I go at a different one. So I'm going to pause here and look at my notes and see what I forgot to say, but I'm not sure there is anything that I forgot to say that I meant to say today. Except to give you a pointer to where we're going. Please, ask lots of questions, because your last two were really useful, so continue.
Just to clarify, so you can only get back to the original B vector if it is connected.
I times V is V. Anything else times V will be something else. So that's step A of what you asked. And there's some subtleties underneath that I actually meant to talk about today. We've talked about inverses, and I've demonstrated a few cases where I have an inverse. A diagonal matrix, a square diagonal matrix where all the stuff on the diagonal is non-zero. I've constructed an inverse in a way that was obvious. Just take all the stuff on the diagonal and make reciprocals. Okay? That's a matrix, that's a square matrix that has an inverse. Okay, so let's talk about the more general concept of inverses. When can they exist? When must they exist? When can't they exist? So how about a 4x5 matrix? Okay, got 4 rows, 5 columns. Takes a vector in, gets something else out. Could it ever possibly have an inverse? Does that even make any sense? You say no. I agree with you. Why no?
Because we cannot get to an identity matrix, like one of the columns will always be 0.
So there's a bunch of stuff hidden in that sentence that's tacit. So I want to make it explicit. Okay? So I got a matrix. This is all going away. Bring me chalk. I'm with Arrow on this one. This is too much work. And noisy. So, suppose I got 4x5. 5. Okay, that's my matrix M. What is the length of vector that goes into this? The input. What's the dimensionality of the input? 5. Okay, so here's 5 numbers. What's the output dimensionality? 4. So M times this is V equals, MV, which is going to have 4. So I had 5 numbers, I only have 4. Am I going to be able to get the 5 numbers back for any set of 5 numbers? So just counting degrees of freedom, impossible. We've lost a dimension. Information has to have been lost that you cannot get back. Okay? If I go from 4 to 5, I may be able to go back. Okay? So if I took M transpose, which is now a 5x4, I might be able to put something over here, A, and I might be able to get the identity. It's possible. took 4 numbers and I scattered them in 5-dimensional space, I might be able to get the 4 numbers back. Now, you know, if M is all filled with all kinds of zeros, that ain't going to be true, because you're going to lose information. But if M somehow preserves the information, I got a 4-dimensional vector and I stick it in a 5-dimensional space where the information is there, I should be able to get it back. So A times M could be the identity. But why is there a transposing? Oh, because I was using, yeah, okay, M prime, some other M. Okay? But what about this? So this went from 4 dimensions to 5 dimensions, and I could get a matrix that goes from 5 to 4 such that I can get everything back. But if I swap the order, here now the first thing I'm doing is going from 5 dimensions down to 4. And I'm not going to be able to get the 5 back. So this ain't going to be the identity. So a matrix is not square. Talking about a true inverse in the sense that you're used to, which is to say it can multiply on the right, it can multiply on the left, and both ways you get something that gives you the identity. That's not possible. So a subtlety that we'll never touch in this course is sometimes you talk about a left inverse or a right inverse. Just a matrix that works only on the left, doesn't work on the right, or vice versa. So we could talk about that. That's the idea of if you move from 4 dimensions to 7, I can get a left inverse that'll get you from 7 back to 4 such that you get the identity. But you can't switch it. So now let's live in the world of 4x4 matrices. Okay? So just we have 4x4 matrix. Now let's talk about inverses. So the diagonals with nothing non-zero on the diagonal, they have inverses. Now in arithmetic, just with scalars and multiply, 0 doesn't have an inverse. Everything else does. In matrices, the matrix filled with zeros obviously doesn't have an inverse. But there's lots of other stuff that doesn't have an inverse. Give me an example that I've already talked about.
If one of the things is 0, right?
Okay, one of the things. So what you're alluding to is, if you have a 4x4 matrix that is diagonal, but if one of those diagonals, at least one of those diagonal entries is 0, you're screwed. Okay? They don't all have to be 0. That's the full matrix of zeros. That obviously doesn't have an inverse. But diagonal matrices that aren't, fancy word, full rank, meaning all 4 are non-zero, if they're not that, they all don't have it. So there's lots of matrices that don't have inverses, even in the land of square matrices. Sometimes there is an inverse, and that is quite useful. And we're going to talk about techniques about, you know, when does it have an inverse, when doesn't it, and how can you tell? And we're going to have a geometry, all of which is what Arrow's going to do next time, that will allow you, in one easy MATLAB call, to get you everything you want to know about whether something's invertible, whether it has a left inverse, whether it has a right inverse, whether what you can do with it, what information is lost, what information isn't lost, what input information is used, what input information isn't used, how much of the output space do you fill and how much don't you. So a diagonal matrix that is taller than it is wide, that creates dimensions, it inserts the input into a bigger dimensional space, but a whole bunch of the dimensions aren't filled. They're all zeros, and they're always going to be zeros, the ones that correspond to the lower part of that matrix that's all filled with zeros. So it goes to an output space, but it doesn't actually fill the output space. Only a subset of the output space can ever be reached with that matrix, and the rest is out of bounds. You can't get there from here. You know, put an input in a vector into this matrix. There are places in the output space you can't get to. In particular, if I have a 7x4 diagonal matrix, the first 4 could do stuff, but the last 3 dimensions are always going to be zeros. So dimension 5, a dimension 5 vector where the 5th dimension has the number 1 in it, you can't get there because this matrix will always have that output be 0. Okay? So we're going to have this notion of how much of the input space is preserved and how much is lost, and how much of the output space is reached and how much can't be reached in a general sense. And the way we're going to get there, and it's a technique that's just awesome, geometrically beautiful, and I'll let Arrow do all the work of talking about it next time, uses this a hell of a lot. So why did I spend all my time talking about subsets of matrices with particular properties? Because it turns out that any matrix whatsoever, a matrix that doesn't look diagonal, doesn't look orthogonal, just filled up with a bunch of numbers, I don't understand what they are, I can decompose that, and that's the piece of what we do next time, into 3 matrices, 2 of which just do this, and 1 of which does that. And so if we understand what these guys do and their properties, we understand all matrices whatsoever, no matter how fancy and complex they might be. Because all they can do is do something like a rotations and flips, do something like changing the coordinate system by doing stretches, and then do something like rotations and flips. That is the thing that we're going to spend all next time. We're not going to prove that, but we're going to show how the geometry works and what we do next time. So Arrow talked about in the very first class. This is a math class. We're going to cover a lot of branches of math, but everything we do builds on what we did previously. So next time, he's going to build on these 2 matrices and what happens when you combine them, and give you a tool that we are going to use for the entire rest of the semester and that you'll use way outside this class, which is a way of thinking about matrices and linear systems that uses these very simple geometric concepts of rotation and diagonal matrices, which just leave the coordinates alone and just you deal with them separately. Okay, I'm going to stop. Yeah, any questions?
So can you prove that for AB equals to I, BA will equals to I for a square matrix?
No, because it's not always true.
Sorry?
Not always true.
What? I mean, if AB equals to I, then
Yeah.
BA
If
equals to
something's
I.
a left inverse, you're asking if it's
No,
a right inverse.
I'm talking about square matrix.
True. Arrow, am I stepping on my...
I remember
Going
the
right
proof
this
is
second?
easy, but I couldn't
Uh,
find it.
no, that is true.
It's not
Yeah,
easy.
sorry, that's true, and we'll be able to prove that with the SVD. Yeah, that'll be obvious from the SVD. Yeah.
So
Yeah,
there's
we'll
no
get there.
simple proof.
Well, we're going to base this whole semester on what's called singular value decomposition, which is what Arrow's going to talk about next time. We're never going to prove that singular value singular value decomposition. We're not going to prove it. Usually it's at the very end, like in this great Strang textbook on linear algebra. It's the last chapter. He gets to it at the end. We're going to jump to it because it's so damn useful. But if you believe or are willing to take on faith SVD, then what you just said pops out for free. So,
But
yes,
actually,
you're right.
it's not more basic than inverse.
Yeah, but I'm not going to... What we are avoiding here is the typical linear algebra textbook approach to linear algebra, which is writing out all of the dot processes, all these double sums of i's and j's that are formulas that just don't illuminate anything, but you can still prove stuff, and going with the geometry. So the geometry of the SVD will answer your question in a way that will be really clear. So I wait until the end of next time to ask the question again, and it'll be kind of obvious. Okay? Let's do it there. Any other questions in the class? Okay. See you on Tuesday every week.